Hello, my name is Joel Swerdel, and in this video I'm going to present a tutorial on how to use the tool PheValuator. During this video I will provide an introduction to PheValuator and the steps in the PheValuator process, including how to create an XSpec and prevalence cohort, how to create the input parameters for the PheValuator run, after the run, how to examine the diagnostics, and finally, how to view the output. Here is a very brief introduction to PheValuator. A more comprehensive review of the tool can be found in the Odyssey library. PheValuator is a tool in the Odyssey Hades tool stack to enable researchers to estimate the performance characteristics of phenotype algorithms. These performance characteristics include sensitivity, specificity, and positive and negative predictive value. There are three main steps in the process. The first step creates a diagnostic predictive model to determine the factors that discriminate subjects who are cases of a health condition from those who are non-cases. The second step applies the model to a large randomly selected group of subjects to create a probabilistic reference standard. The third step tests the phenotype algorithm against this probabilistic reference standard to obtain performance characteristics.
We will now create the cohorts necessary for the PheValuator run. The first cohort we need is the XSpec cohort. The XSpec cohort is used to create a cohort of subjects, each with a very high probability of having the health condition of interest. The example we will be using in this tutorial is for end-stage renal disease. The cohort entry event is a condition occurrence of end-stage renal disease, with a continuous observation period of 0 days prior to the condition occurrence and 365 days after. We are also looking for all events of this condition. To make this cohort very specific for end-stage renal disease, we add two inclusion criteria. The first allows subjects to enter the cohort if they have either of these criteria. Either the subject has a procedure for end-stage renal disease on the same day as the condition occurrence of end-stage renal disease, or the subject has both of the following: a condition code for end-stage renal disease for the first time in their history, up to 14 days prior to the entry event, and the subject has at least two condition codes for end-stage renal disease in the 14 days prior, where these conditions occur on two separate days. Adding in these criteria make the subject very likely to have a high probability of having end-stage renal disease. We also add an exclusion criteria to eliminate subjects who may have other similar conditions. To be included in this cohort, the subjects must not have any of these conditions in the 7 days prior to index through the 30 days after index. The excluded is a long list of conditions, all of which were mentioned as differential diagnoses as found in stat pearls. We next need to create the prevalence cohort. The prevalence cohort is used to create a cohort of subjects to provide an estimate of the prevalence of the health condition in the population, and this is going to be used when we recalibrate our model. For our end-stage renal disease analysis, the cohort definition looks like this. It's a rather simple cohort. We include subjects who have a condition occurrence of end-stage renal disease for the first time in the subject's history. We don't require any defined continuous observation time, and we are looking for the earliest event in the subject's history. This definition will allow us to get all the subjects who have a condition code for end-stage renal disease, and allows us to estimate the prevalence of end-stage renal disease in the database population. Now, using RStudio, we will develop the R script to run PheValuator for end-stage renal disease. I set some options prior to each run, including setting the Java memory to 64 gigabytes or whatever your system can handle. I then create the input parameters for the PheValuator functions, including setting the XSpec and prevalence cohorts. For the cases used in the model, PheValuator chooses a visit for a subject in the XSpec cohort just after the index date. You set the days from XSpec to be the maximum number of days from 1 day after the index date that a starting visit is allowed. For chronic conditions, this is usually set to 14 days, so that the designated start visit can be in the range of 1 day after the expect index date until 14 days after the expect visit. The excluded covariate concept IDs are the list of concept IDs that were used in the exclusion criteria in the expect cohort. Remember, any criteria that impinges on the days after index in the expect cohort must be excluded from the model process. Give the phenotype you are running a name and create an output folder for the results. We next set the create default covariate settings parameter. These are critical to set the windows for the prediction model. For chronic disease, we usually use these settings, where window 1 is from 0 to 30 days from the designated visit start date, window 2 is from 31 to 60 days after, and visit 3, 61 to 365 days after. We generally set the add descendants to exclude to be true. This will also remove the descendants of the excluded covariates from the modeling process. This may be changed to false if there are some descendants you do not want to exclude in which case you should exclude all the covariates individually. Next, we set the parameters for the create evaluation cohort args. Most of these are straightforward. We found these model, expect, and evaluation cohort-based sample sizes to work well. Note, these are maximum numbers and your data set may use smaller sizes. The final parameters to set are for the phenotype algorithms to assess using two functions. The first, create test phenotype algorithm args, sets the phenotype ID and also the washout period. The washout period is generally set to 0 unless you define a specific observation washout period length prior to the subject's index date. The second function, create PheValuator analysis, creates the specific analysis to run, names the cohort for display, and uses the parameters previously set. You then create a list of the analyses you wish to run. In this case, it is for 4 analyses to test. I like to set up my database connection in a list where I can reuse the component parts. Set up your connections with the CDM database schema, cohort database schema, etc. appropriate for your system. Finally, we set up the actual PheValuator run through the run PheValuator analysis function. Name the phenotype you are testing, add in the database connection parameters, supply a folder to receive the output, and provide the analysis list from above, and you are good to go. After the run, you can review the results using the summarize PheValuator analyses function. After the PheValuator run, you can review the diagnostics. Reviewing the diagnostics is important as it may give you some indication of whether you have missed important covariates in your definitions. Here is an example of what your output from PheValuator will look like. To review diagnostics, we will examine the export folder. The export folder has all the diagnostics you will need. The first diagnostic to check is the model covariates file. This file gives you the main analysis settings and the model covariates along with their beta coefficients. You want to examine the model covariates to ensure they seem appropriate and that nothing was included in the model that shouldn't have been. So when reviewing the model, we note a couple things. One, we see the 3 different windows that we set, 0 to 30 days, 61 to 365 days, 31 to 60 days. These include all the different features that were important in those different windows. We also note that end-stage renal disease and chronic kidney disease stage 5 play prominent roles in the model. They're the largest covariates at a couple different time points. One other thing to note is that renal failure syndrome, which wasn't included in the phenotype, is also has a high beta coefficient and is a strong predictor for end-stage renal disease. We can now look at the possible errors in the phenotype definitions by looking at examples of false negative subjects and false positive subjects. To find these subjects, we examine the subject's covariate file. This file provides the main analysis settings and a subset of subjects classified as false negative or positive and true negative and positive, along with the model covariates present in the subject's record contributing to their predicted probability of condition. For example, this subject, and this is all the data for this same subject, this subject was designated a possible false negative based on his predicted probability for having end-stage renal disease. Some of the covariates from the model present in this subject are that they were using a nursing facility, that they had renal failure syndrome, that they had comorbid renal impairment, they had kidney disease. If you look at the patient profile from Atlas for this subject, we can see it appears this subject was in renal failure for an extended period of time. Using this patient's profile and a high predicted probability for end-stage renal disease, we may consider adding renal failure syndrome as a covariate in our cohort definition. Using the same file, we can also look at possible false positives. This subject had a very low predicted probability for end-stage renal disease, but did have a code for chronic kidney disease, stage 5, which is what we were looking for in the definition. When we look at this subject's patient profile, we see that the subject had chronic kidney disease stage 5, but in the middle of other stages of chronic kidney disease, including stage 1 and stage 3. Based on this subject, we might consider chronic kidney disease stage 5 to be misclassified and think of ways to represent chronic kidney disease stage 5 differently to improve the positive predictive value, or PPV. For example, we might consider requiring a second diagnosis of chronic kidney disease stage 5 within a month after the first diagnosis to improve the PPV. The issue with doing that is that while it would likely improve positive predictive value, it will likely decrease sensitivity and will also introduce immortal time, so there is a trade-off. Now we're ready to examine the results from the PheValuator run. Remember, the goal of PheValuator is to estimate the performance characteristics of phenotype algorithms we are considering in our study. The results from the analysis for each of the data sources can be found in the algorithm performance results in the export folder. I've coalesced the results from multiple databases into one file to compare the results. To remind us of the differences in the definitions, we can go to Atlas. The first definition was the simple prevalence cohort we developed earlier that looked for condition occurrences only. The second definition was the most complicated and included measurements and dialysis procedures. The third definition looked for conditions, observations, and procedures. The results show the database, describe the cohort, give the cohort ID, and present the sensitivity, positive predictive value, specificity, and negative predictive value. What we see is that in the simple cohort, the prevalence cohort provides very similar results to the third cohort using conditions, observations, and procedures. In most of the databases, these two tend to do slightly better in both sensitivity and positive predictive value than the complex cohort, though generally within the range of the 95% confidence intervals. The exception is JMDC, the Japanese health insurance dataset, where the most complex cohort definition improves the sensitivity at a small cost of positive predictive value. Thank you for listening to this tutorial on using PheValuator. If you have any questions, please let me know by emailing me at the address shown on the screen.